Okay, I had to step away for a minute, so I'm still learning this system, so I'm just going to start a second video. We'll put them together into one, and I'll figure this out. This is kind of a new challenge for me. Anyway, we were talking about, I was saying air, I can't spell, air is a mixture. All right, I've got room, I added a piece of paper. So air is a mixture of, let's think about what's in air. Air, there is nitrogen. Actually, air is 78% nitrogen, and we represent nitrogen chemically as N2. 21% of air is oxygen, which we, of course, as humans need to breathe. That's O2. We exhale carbon dioxide, which is CO2. There's a little bit of water vapor in there, which is H2O. And there's actually some other trace elements, things like helium, and I'm just going to stop there because this is quite a lot of stuff to go into one mixture that we're going to try to draw. All right, so if I were going to draw this, and I'm going to draw a great big box. All right, let's say that I represent nitrogen. A nitrogen atom is a triangle. An oxygen atom, I'm going to make a circle. I've got carbon, I'm going to make carbon a square. I've got hydrogen, let's make hydrogen a diamond. And then I have helium, let's make helium an oval. All right, so here's my key. Now I'm gonna draw this. So each nitrogen is N2, so that would be represented like this, with two triangles connected or bonded together. All right, oxygen is O2, so this would be represented as two oxygen atoms bonded together. Let's see, CO2 is going to be carbon, so a square plus two oxygen. So carbon is a square. And then I have two oxygen bonded to it. Let's see, hydrogen, so water would be two diamonds and a circle, so H2 and one circle. All right, and finally, helium is an oval, so I'm going to stick some helium in here. So this is a mixture, and the way that I've drawn it, it's a heterogeneous mixture because there's no order to it, okay? And you could make an argument either way for air. It could either be classified as a homogeneous mixture because what we see all looks the same, but it could be classified as heterogeneous because where there are more people, there's going to be more carbon dioxide. So I would take either answer for air as in terms of homogeneous or heterogeneous. Now, I'm getting ahead of myself because we haven't even defined homogeneous or heterogeneous. We've just defined a mixture as a combination, a physical combination of two or more elements and compounds. Okay, and the key here is that the mixtures can be separated. Like we can filter something off, we can evaporate something away, we can sort, we can actually take the pieces apart. Whereas in a compound, those atoms are bonded together and we can't get them apart. So let's look at the two types of mixtures. We have homogeneous and we have heterogeneous. I heard a lot of you using words from biology like homozygous, heterozygous, so you kind of get the idea that homo means same, hetero means different, okay? When we talk about homogeneous mixtures, what we're saying is, where they get the same, is they are the same throughout. Another really good word is uniform. Okay, so basically what this means is that in all parts of the sample of the substance, the different parts of the mixtures, the atoms and the compounds, are distributed evenly. So, for example, we might take an example of, let's just say, two elements mixed together. So let's say we have a combination, actually brass. Let's do brass, because brass is not an element. It's a combination of copper atoms and zinc atoms. Now, if I wrote this with formulas, I would do Cu, that's copper, and zinc. Okay, I would not put Cu and Zn together because that would tell me they're bonded together, and that would make me think that that's a compound, not a mixture. So if I was going to draw a sample of brass, let's say that zinc is a let's say zinc is a diamond, and copper is a diamond, and zinc is a circle. Okay, so if this is a homogeneous mixture, what that means is there's going to be order to it. Wherever I look in the sample, if I look at it on a particle basis, it's all going to look the same. Okay, it's uniform throughout the entire sample. In other words, the atoms, or the compounds in some cases, are evenly distributed. Okay, so let's think about an example, a real life example. So one that I like to use is Kool-Aid. All right, so if I make a pitcher of Kool-Aid, Kool-Aid is made of water, which is a compound, and sugar. So let's think about this a little bit. I have to move my paper over. There we go. Water and sugar, which is another compound. And then it's also got a bunch of other things, like the flavoring. So let's just put color and flavor. So whatever the stuff is that's in that packet, it's got more than one substance in it. It's a combination in itself. So let's say we make a pitcher of Kool-Aid. This is where we find out that Mrs. Lyons can't draw very well. So here's a pitcher of Kool-Aid, except it's not showing up. Hold on, there we go. So if we have a pitcher of Kool-Aid, so I put in the water, I put in the sugar, I put in the Kool-Aid mix, and I stir it all around, all right? And if it's mixed completely, okay, if I pour you a glass and I pour me a glass, they're going to be the same, because the solution, another word for a homogeneous mixture, was completely the same throughout. Okay? So that makes that homogeneous. Another good example that we can do an exact comparison is orange juice with pulp or without pulp. So if you think about orange juice, if you get it without pulp, it's going to be a homogeneous mixture, because you really can't tell the difference. If you pour me a glass and I pour you a glass, it's the same substance. It's going to have the same amount of stuff in it because it's mixed uniformly. Okay, we'll talk about without pulp here in just a minute. So let me get a new sheet, and let's talk about heterogeneous mixtures. So a heterogeneous mixture is a mixture that is not uniform. Okay, so there's different parts in it. It's still made up of a variety of compounds and elements, and it's still mixed together. It still can be separated, but it's not the same throughout. So one of the things I think about is if you've ever had oil and vinegar salad dressing. It's kind of like putting oil and water together. If you've ever done this, you notice that when you put them together into a container, you get a layer. And what happens is the vinegar, because it's water-based, is on the bottom, and the oil settles on top. Okay, so there's two distinct parts of this mixture. If you think back to the particle pictures we drew with that activity, let's say that the oil, and we're going to have to make it more than one thing, but so let's just, for the sake of it, let's say oil is a shape. So don't think of oil as a single atom. We're just going to say that oil is a circle and vinegar is a triangle. Okay, so we said the vinegar sinks to the bottom. So what that tells us is we would have a layer, and again, don't think about these as being elements like we did earlier, but just think about them as parts of a mixture. Okay, so the oil or the vinegar would be on the bottom, and then the oil would settle on the top. So if we drew a particle picture, this is what it would look like. Okay, you wouldn't have it evenly spread. All right, another example we used, if we have Lucky Charms. If I pour you a bowl of Lucky Charms and I pour me a bowl of Lucky Charms, there's no pattern. It's very random. I may get a ton of marshmallows and you may get none, okay? Which that in and of itself makes it a heterogeneous mixture. So I hope this helps a little bit. I will get these posted on Haiku. You can look at these. If you have questions, I will see you in class.